Hello everyone, welcome to the second video of week 5. In the previous video we introduced the simple linear regression model for a dataset consisting of pairs x, y. The model makes several assumptions. To start with, it assumes that a straight line captures the relationship between the x and the y variable. And in addition, it makes a number of assumptions on the measurement errors. In this video, you will learn some numerical and graphical methods to check whether these assumptions are reasonable and to assess the quality of the fit. The key ingredient for these methods are the residuals. Now let alpha hat and beta hat be the least squares estimates. Then, for each observation, the corresponding residual is defined as the difference between the value of y and the value alpha hat plus beta hat times x. It represents the difference between the observed value of y and the fitted value of y that we would get on the basis of the estimated regression line. In fact, these are exactly the vertical distances of the points in the scatter plot towards the estimated regression line. Now, how can we use these residuals? Well, recall that alpha hat and beta hat are unbiased estimators for the true alpha and beta. This means that the ith residual is approximately equal to the ith measurement error. And for this reason, the residuals mimic the unobservable measurement errors. And therefore, we can use them to check the assumptions of the model. Now, we will do this by means of residual plots. Let me explain the first one. According to the model assumptions, the observed y variable is equal to a measurement error added to the linear relationship with the x variable. Furthermore, these measurement errors are assumed to have a mean zero and the same variance. This means that if we plot the values alpha plus beta times x on the horizontal axis against the measurement error on the vertical axis, we should find points evenly scattered around zero in vertical direction. Now, of course, we cannot do this since we do not know the true alpha and beta and we do not observe the measurement errors. However, we can mimic this graph by plotting the fitted values on the horizontal axis against the residuals on the vertical axis. Now, here is such a plot for the mortality example of the previous video. The residuals are scattered more or less evenly around zero. This seems to support a linear relationship between mortality and calcium concentration and also supports the assumption of zero mean for the measurement error. Now, furthermore, going from left to right, the amount of variation in vertical direction is more or less the same. So this supports the assumption of equal variances for the measurement errors. One usually refers to this property as homoscedastic errors. This in contrast to heteroscedastic errors, which refers to measurement errors for which the variance depends on the x variable. So the linear relationship and the moment conditions on the measurement errors are supported by the residual plot. What about the assumption of a normal distribution for the measurement error? Well, this can be checked either by a histogram of the residuals or by a normal QQ plot of the residuals. Well, here is a normal QQ plot for the residuals in the mortality example. They are more or less on a straight line, so that the assumption of normality seems reasonable. Now, the two plots we just showed you are part of the standard plots that can be extracted from the fitted LM object, say myLM. Just type plot of myLM. And this opens a dialog in the console. And every time you hit the return key, it produces a standard graph. After hitting the return key, a plot appears, which is the first residual plot we just discussed. Note that a smooth curve has been added to the residual plot. It is constructed by taking some sort of moving weighted average of the points in the plot. The more horizontal it is, the more it confirms the linear relationship and the mean zero assumption on the measurement error. After hitting the return key, a second plot appears. And this is the normal QQ plot with a straight line added. Now, the remaining plots are beyond the scope of this MOOC, so we leave the dialog line by pressing escape. Now that we have convinced ourselves that the assumptions of the model are reasonable, we will quantify the quality of the fit. And this is done by means of comparing sums of squares. Now recall that the variation in the y variable can be quantified by the sample variance. Now here the factor 1 over n minus 1 is irrelevant, so we can also quantify the variation simply by the sum of the square differences with the sample mean. This sum of squares is called the total sum of squares. It represents the total amount of variation in the y variable. Now this variation has two sources. Let me explain what I mean. Suppose that there is no measurement error, so that all points lie exactly on a line that models the linear relationship between x and y. Then if we focus on the y values themselves on the vertical axis, we see that if x and y are linearly related, then even without measurement error, this causes variation in the y variable. The other situation is when we only have measurement error and y is not affected by the variable x. This would correspond to a horizontal regression line with the y values scattered around it. Again, if we focus on the y values itself on the vertical axis, we see that this also causes variation in the y variable. So there are two sources that cause variation in the y variable, and we are dealing with a combination of the two. One source of variation in y is due to measurement error, and the other source of variation is due to the linear relationship with x. Now recall that the observed variation in y is represented by the total sum of squares. In the same way, the amount of variation due to measurement error is quantified by the so-called residual sum of squares. And the remaining variation in y is due to the linear relationship with x. And the more this is a part of the total variation, the better the fit. So this leads to the coefficient of determination that can be used to assess the quality of the fit. It is defined as 1 minus the proportion of variation in y due to measurement error. It is usually denoted by r squared, and this is due to the property that the expression turns out to be equal to the squared correlation coefficient between x and y. It represents the proportion of variation in the y variable that is due to the linear relationship with x. And for this reason, it is referred to as the proportion of explained variance. The closer this proportion is to 1, the better is the quality of the fit. Now all these quantities can be extracted from the fitted LM object. And let me illustrate things by means of the mortality example. The different sum of squares can be found by applying the function ANOVA to the fitted object. And here ANOVA stands for analysis of variance. Running this function generates output that contains the so-called ANOVA table. It contains all sorts of information, but for the moment we focus on the sums of squares contained in the second column. In the row named residuals, you can find the residual sum of squares. And in the row named calcium, you can find the sum of squares due to the linear relationship between mortality and calcium concentration. Together, they form the total sum of squares. Well, we can already see that the majority of the variation in the y variable is due to measurement error. And this will result in a small value of r squared. Well, the exact value of r squared can be found by running the function summary on the fitted LM object. Running this r function produces the following output. This contains all sorts of information about the linear fit, such as the estimates for the intercept and slope, but also the r squared, which is 0.4288. This means that only 43% of the variation in the variable mortality is explained by a linear relationship with calcium. So most of the variation in the variable mortality is due to measurement error. Finally, the estimate for sigma can also be found in this table under the name residual standard error. It turns out to be 143. The least squares estimate for the variance of the measurement error is the square of this. But it can also be found in the ANOVA table. The first column of this table contains the so-called degrees of freedom. And for the residuals, this is precisely n-2, in our case 59. And the third column is the ratio of column 2 divided by column 1. Hence, the mean square residual is the residual sum of squares divided by n-2. And this is, by definition, the least squares estimate for sigma squared. You may check that if you take the square root of this, you will find 143. Now that we have convinced ourselves that mortality is linearly related to calcium concentration, how can we use the fitted linear regression model to answer all kinds of research questions? For example, is the estimated slope negative large enough to conclude that higher calcium concentrations lead to a decrease in mortality? Well, this will be the topic of the next video, in which we will discuss tests and confidence intervals for the linear regression model. See you then.